Just a moment.
Окей. Я вас вітаю на нашому черговому засіданні Вільного університету Майдан Моніторинг. І сьогоднішнє засідання, сьогоднішня лекція в нас досить незвичайна, тому що не тільки тому, що наш лектор на зв'язку з іншої країни, але і лекція сьогодні відбуватиметься англійською мовою. So welcome to our Free University meeting, and today we have quite unusual lecture because it's from foreigner speaker, and also it will be in English. І сьогоднішня тема називається енергоефективне будівництво. І це дуже актуальна тема не тільки в світовому контексті, але й конкретно для України, тому що ми зараз стикаємось з реальними цінами на паливо і розуміємо, що дуже дорого опалювати наші діряві будинки. Тож давайте послухаємо думку експерта. So today the topic is the energy efficiency in building, and it's an important topic for Ukraine because now we faced problem with fuels, and we understood that it's quite expensive to heat our old buildings. І лекція, значить, сьогоднішній лектор Марко Пінтерич з університету Марібор зі Словенії. So our speaker today is Marko Pintaric from the University of Maribor, Slovenia. І він розкаже нам цю тему з точки зору фізики. And he will present this topic from the physicist point of view. So welcome, and let's start.
Okay, thank you for invitation. I'm honored that I'm first English speaker in your Maidan Monitoring Free University. I was already introduced, so maybe I'll start immediately. I will now show you. I don't see this presentation. It's not here. I hope that okay, here it is. So I will start my presentation, which is, as you are already well told, is about building energy efficiency. Do you see the presentation?
Yes, yes,
okay.
It's very clear.
Okay, so as the presenter told you, I'm from Maribor. Actually, I'm now calling from Zagreb, Croatia. I'm doing some measurements here, so the beauty of the internet is that we can move from place to place and can still be in contact. So let's begin with my presentation. Okay, first of all, I will show you this table of contents. We will have 5 chapters. I will try not to do too much theoretical part. I'll try to do some things, some more applicative approach. So what should be done and what is already done, especially from the point of view of European Union. So first we will start some general discussion about energy efficiency in general. In the chapter 1, in the second chapter, this is most theoretical chapter. We will talk about mechanisms of heat transfer. You need to know some basic theory in order to understand the rest. Okay, in the third chapter, we will join these mechanisms of heat transfer together to understand heat transfer in individual building components. And in the fourth chapter, we will join these individual building components together to understand the complete thermal losses of the building. So we are building a pyramid. We are going from the basement to the roof. And in the end, in chapter 5, I will show you some final remarks. Okay, so there are many problems related to energy. So some are very obvious. For example, if you are spending a lot of energy, you're also spending a lot of money. So big spending of energy means big financial cost. Okay. The second problem is, of course, limited resources. This is, of course, global problem. We all know that fossil fuels like gas or coal or oil, they are limited. So we know that we cannot keep spending in this pace as we are spending right now. And the third problem is ecology. So very popular topic today in the world is global warming. Of course, there are a lot of discussion and a lot of controversy about global warming. Some people, including President of the United States, claim that this is a big hoax. But my counter-argument is that even if it would be, even if it was a hoax, there are still plenty of other reasons why we want to do something about spending energy and using another types of energy. First of all, there is energy independence. I think that this is important topic in European Union, and it is important topic in Ukraine. And of course, don't forget that this energy efficiency, this also creates new kinds of jobs, especially local jobs. I will tell you about this later. Of course, it is important that we have and then better environment, cleaner environment. And I take a liberty to change this cartoon a little bit. I added the last one. Of course, you all know that there are certain countries which live from selling fossil fuels, and one of those countries is very hostile to Ukraine. So Ukraine has many things to be considered about, concerned about regarding the spending of energy. Okay, so maybe I will provide you in the beginning some solutions to energy-related problems. Okay, the most obvious solution is new energy sources. So we can use renewable sources like hydro, sunlight, wind. Of course, we know that in the present moment, in this present technology, these sources might not be enough to replace fossil fuels. Then we have nuclear energy sources. We have fusion, which is already, we are using it a lot, but of course it is problematic because we have radioactive waste. We don't know what to do with this waste. We have fusion, but fusion is also technology of the future. So these new energy sources are still some kind of, in many terms, are still future solutions. So what are current solutions? What can we do today? Today, we can increase production efficiency. So first of all, we can recycle materials. Okay, it is much more cheap to make copper from waste copper than from copper ore. So when you produce plastic metals and everything else, if you using waste materials, it is cheaper. You need less energy than if you produce from the basic sources. Okay, the second possibility is reusing energy. Typical situation is power plants. You know that power plants, we produce electricity, and these power plants have waste heat, and we can use this waste heat to heat residential areas, to heat houses, and this is called cogeneration, combined heat and power, CHP. And this is already common in European Union. I think that this is even common in Ukraine. And a little bit more futuristic is tree generation, because you can also use this waste heat even to cool residential areas. Okay, so what is the point? The point is that we use the same energy twice. We use this same energy to produce electricity, and we can also use this energy to heat residential areas. And the final point is consumption efficiency. So we all know that, for example, if we use public transport, we use less energy than if we are traveling individually by car. This is very common situation in Europe. What is the main point of our lecture is reduced energy losses. So this one particular part will be of most concern in my lecture. Okay, let's put some numbers into this discussion. Okay, this is data for European Union, 2012 by sector. We see that most of energy is used by transport sector, then it is industry sector, households and services. This is not very surprising, but what you will find surprising is if I show you this, you see that how much energy is used only for heating and cooling. So you see 84% of energy for households is used for heating and cooling. For industry, 74%. Services, 63%. So if we add this all together, we see that we are, that in European Union, of course, at least, 50% of all final energy is consumed for heating and cooling. So heating and cooling is obviously big consumer of energy. Okay, so maybe we go beyond that and see what is this heating cooling coming from. Here is by category. You see that 52% of this heating cooling energy is used for space heating. So heating the rooms we are living, the apartments we are living, offices we are living. Space heating is half of this energy. Then, of course, we have space cooling, 2%, and water heating. All these three categories are connected to houses. So then, of course, we have process heating, process cooling. This is about an industry, and we have others. If we add this all together, we see that, first of all, I would like to point out that space cooling and process cooling is growing very fast. So these two percentages are growing very fast because today, you know, air conditioning is completely normal, usual everywhere. About now, by maybe 20, 30 years, it was not so usual. So people are starting to cool their houses. So space cooling and process cooling are growing very fast. All in all, building heating and cooling or energy used by buildings is 31% of all final energy consumption. So what is here important? Which are the important factors which can contribute to larger or smaller consumption? First of all, there is efficiency of building thermal envelope. So how much energy we lose through the walls? This is very obvious. Okay, this is the most important in our lecture. The second is efficiency of heating and cooling equipment. You all have boilers or maybe furnaces to warm your water and buildings. And these, if these devices are old, they don't have high efficiency. So they also have to be replaced from time to time to keep the high efficiency. And also there is behavior of occupants. If you reduce temperature in the room in your apartment for few Celsius, then of course you lose much less energy. Okay, this is not very popular, but it is also a possibility. Okay, so now when I describe these problems, we will now concentrate on this losing energy through the walls, losing the energy because of the house envelope. Okay, I will not go into big theory, but I must say that there are three mechanisms of heat transfer. The first one is conduction. So what is the conduction about? The heat is transferred by particles. And these particles cannot travel. They can only oscillate. So when they oscillate, they collide between themselves, and by these collisions, the heat is transferred from the hot side on the left to the cold side on the right. And of course, where are the particles that cannot travel? In the solids. In the solids, for example, in the wall, in the glass, you have particles that cannot move. They can only oscillate, and there is only possibility of conduction. The second mechanism is convection. Again, we have particles, but in this case, particles can move, they can travel. Okay, so for example, as in this case, particles are circulating within some kind of place, and they are transferring again, where they are transferring heat from the hot side on the left side to the cold side on the right side. Okay, where is the possibility that particles can move? In fluids. In liquids and gases, particles can move. So this convection appears in fluids, generally in fluids. And we have the third mechanism of heat transfer, and this third mechanism is radiation. So what is radiation about? Radiation is about electromagnetic waves. So there are particles are not necessary. And electromagnetic waves are emitted by practically all bodies in the universe. First of all, where can radiation appear? In empty space, because electromagnetic waves can travel very easily to empty space, either through vacuum or either through air. There is one important thing to know about radiation, is that because all bodies radiate, so sun radiates, we are radiating, so it means that energy goes or heat goes both ways. Okay, energy goes from hotter side to the colder side, and energy goes also from the colder side to the hotter side. Electromagnetic waves are traveling in both directions. Of course, there is some difference, because bodies at higher temperature, they radiate more, and bodies at lower temperature radiate less. Also, as it's seen in this presentation, bodies with high temperature, they radiate short wavelength. You see these short wavelengths, and lower temperature bodies, they radiate long wavelength. Of course, because bodies with higher temperature radiate more than bodies at lower temperature, this means that then net heat transfer goes from the hotter body to the colder body. Okay, so this radiation is very interesting. We can understand many common things around us using the knowledge of radiation. Let's see two applications of the radiation. First application is thermography. Okay, so I already told you, depending on the temperature of the surface, you have more radiation or less radiation. You have short wavelength or long wavelength radiation. So if you use this information, you can measure temperature without a contact. You can make contactless measurement of temperature. This is used by thermographic cameras, which, for example, there are examples of measurement with thermographic camera. I have found in Maribor one building which is partly insulated. So this is old part of the building. There is new part of the building. So what you see here is a real picture, and you have infrared picture. Infrared picture shows you hotter and colder places. So yellow is high temperature, and blue is low temperature. So what you see is that that bad insulation means high temperature on the surface, and good insulation means low temperature on the surface. Of course, we have seen that here we have large thermal losses and we have small thermal losses. So only by using this camera, only by making a picture, you can immediately see if insulation is good or not good, and if there are weak points in the insulation and so on. The second application of the radiation is, of course, understanding of greenhouse effect. The greenhouse effect is something that even children in the school are learning, and in my experience, usually it is not explained properly. I will try to explain greenhouse effect properly, because we will use this greenhouse effect in the end of the lecture. So the effect of greenhouse effect is based on special characteristic of glass. So we have glass here in between. So typical situation is, for example, you have sun on one side of the glass and you have a chair which is in the room, okay? And you put this chair next to the window, of course. So what happens is we know that sun has temperature of about 5,800 kelvins. So this means that it radiates short wavelengths. It radiates visual spectrum, visual light, okay? So this visual light, it can go through the window practically unobstructed. On the other hand, we have chair, and this chair has only 300 Kelvin. This chair, of course, is heated by sun. If you put a chair next to the window, you will see that this chair heats up, okay? It gets higher temperature, but it only heats up to about room temperature. Room temperature is about 300 kelvins. So it has low temperature, and because a chair has low temperature, it only radiates long wavelengths. And these long wavelengths cannot go through the window. They are actually absorbed by the glass, and part of this energy is returned back to the room, and part of this energy goes into environment. So you see, radiation can go practically unobstructed in the room, and energy cannot completely leave the room. So transfer is unobstructed only in one direction. The same greenhouse effect is valid for the planet, Earth as a whole. And the function of glass is atmosphere, or more particular, greenhouse gases like carbon dioxide and others, okay? So this carbon dioxide, it's function like a glass. It lets radiation from the sun in, and it obstructs radiation to go from the Earth back to the space. Okay, so this is the real explanation of greenhouse effect. Okay, let's go now. Now we were introduced with basic mechanism of heat transfer, and now we will join these mechanisms to understand how the heat is transferred through the wall. Okay, first there is a basic formula. I will not go into details, but formula is very obvious. You know, this is how much heat is transferred to the wall. Of course, this is proportional to the wall area. Bigger wall means more heat is lost. Okay, then of course it depends on temperature difference. This is external temperature, this is internal temperature. The bigger difference of temperature means larger losses. And of course, here in the middle, we have so-called thermal transmittance. And this thermal transmittance is characteristic of the wall. This is what we can influence. We cannot make, of course, we can make walls smaller, but this is not very practical. We cannot change temperature outside and inside, but what we really can do, we can change this thermal transmittance. So to understand this formula for thermal transmittance, we only have to put individual mechanisms of heat transfer. Let's start with the first mechanism. First mechanism is conduction. Okay, conduction appears only in solids. So conduction obviously appears in the wall. In the wall, here there is a conduction. Okay, I didn't explain the picture completely. We have external environment, we have internal environment, and you have wall in between. Okay, except for the conduction, we have, of course, short wavelength radiation. In case of the non-transparent wall, of course, short wavelengths cannot go through the wall, so they are stopped by the wall. More interesting part is long wavelength radiation. So we have a thermal exchange between external environment and the wall, and we have thermal exchange between internal environment and the wall. And finally, we have, of course, the missing one is the conduction. Conduction appears only where you have gas. You have air and inside, and you have air outside. So convection can appear inside and outside.
Some problems. The sound actually has gone. Can you have a small pause, please?
Витя, включи микрофон, ёлки. Ну, да, включи, бо я не можу включити.
Okay, I will tell you when we can move on, when we
We will try to turn off the microphone. It's my error. I'm sorry.
okay, just one more minute, please.
Marco, we have some problems with microphone. I'm trying to fix it. I don't know actually how to what to do with it, but Marco, if you hear me, can you exit the room and doing it again, the hangout? Oh,
Hello?
Marco,
Hello?
Marco, say something, please.
I'm saying hello.
Oh, great, great. Oh,
Okay,
we
hi
can
again.
continue. I'm very sorry for the problem. So
Okay.
please continue.
Okay.
So we stopped when you was telling about radiation mechanism inside wall, inside interior, and
So maybe I go just to
the
one
next
little.
slide.
Okay. Like here. From here on.
The next.
Here.
Okay, here.
Okay. So the next mechanism is long wavelength radiation. It appears in the gases. We have air inside in the internal environment. We have air in the external environment. So we have, pardon me, radiation appears in empty spaces. So it appears in the internal and external environment. And it provides exchange of heat between the internal environment and the wall, and on the other side, it provides thermal exchange between external environment and the wall. And of course, the last missing mechanism of heat transfer is convection. Convection appears in the gases, and of course, we know that we have air on the both sides of the wall. So here, convection transfers heat between internal environment and the wall, and here convection transfers heat between external environment and the wall. So how we want to put these mechanisms together? We see that here convection and radiation work together to transfer heat between external environment and the wall. We see this in this formula. Convection and radiation together make something that is called external surface resistance. This is external surface resistance. On the other hand, convection and radiation here work together. So we get internal surface resistance. This formula here is internal surface resistance. And of course, in the end, we have to join to the formula also the conduction. So this is the final formula. We have external surface resistance, we have conduction part, and we have internal surface resistance. So you see that this formula is really not very complicated. It only describes the picture. All these mechanisms in this picture come together into this formula. Of course, more interesting situation is double glazed window. This is why I really put the previous slide, because this is a little bit more complicated, but it's also more interesting. So first of all, we start with conduction. Conduction can only appear in the glass. Okay, so double glazed window means glass. Between glass, we have some space. And of course, we have external environment and we have internal environment. Okay, then we have short wavelength radiation. As before, unlike before, short wavelength radiation can go through the window and it can warm up the chair, for example, or the wall in the room. Okay, then we have long wave radiation. Long wave radiation also appears in the airspace because it transfers heat between one glass and the other glass. So heat between those two glasses is transferred by long wave radiation. And finally, we have convection. Convection also appears in airspace. And because in airspace, we have some gas, usually in all windows, we had normal air. Okay, so this air is circulating between these two glasses, and by this convection, heat is transferred between two glasses. Okay, so this formula is a little bit changed a bit. You see, we have external surface resistance, we have conduction through one glass, we have thermal resistance of airspace. Thermal resistance of airspace is combined of conduction and radiation. We have heat transfer due to conduction through the second glass, and we have internal surface resistance. Okay, and now the question is, how can we improve the window? We, of course, we could make the glass thicker, but this is not very useful. Why not? Because glass is very good conductor, heat conductor. So it is a little bit worse than metal, but if you make glass very thick, it will still conduct a lot of heat. Okay, so we cannot. So this is not an option. We cannot influence radiation and convection outside. We cannot influence convection radiation inside. So the only way we can influence the effect and improve the window is if we change radiation and convection between the glasses. This is the point. Only this can be improved. Of course, the other possibility is that we add another glass. We can have triple glazed window. This is, I will talk about this in the end. Okay, so how can we reduce radiation and convection between two glass two glass layers? Let us see this in this next slide. So this is normal situation. We have two glasses. We have air between glasses. So we see that thermal transmittance is about 2.8. What we can do? First we can do is we can replace air by argon and other noble gases. So there is big physics behind this, but let me try to explain very simply. So argon atoms are much heavier than air molecules, and argon has fewer orders of freedom, so they cannot transfer so much energy. So because if you put argon instead of air, we influence convection, we reduce convection. So by replacing air with argon, we get 2.7 for thermal transmittance. The second possibility is that we put some metal coating on the glass. This here is metal coating. So what is metal coating? This is very, very, very thin, micrometer thin layer of metal. So you can still look normally through the window, but what will happen because of this coating? The long wavelength radiation will be completely reflected. So this influences radiation. If we put this coating, metal coating on one side, we will get thermal transmittance of only 1.7. So we reduce radiation. Of course, we can combine, we can reduce convection and radiation, and we can get typical window which is sold in European Union. I mean, I think this is also normal to to buy this window in Ukraine. So we put argon and metallic layer, and we reduced convection, we reduced radiation, and we reduced thermal losses by half. Okay, so you see how understanding of basic mechanisms of heat transfer can explain what is the point of so-called low E or low energy or low emittivity windows which are sold on the market today. Okay, the next concept which is important and is connected to these thermal losses are so-called thermal bridges. So thermal bridges are weak points on thermal envelope. So thermal envelope, of course, is this wall which closes the house. So weak points. I think that there are certain points on the thermal envelope where heat flow is much larger than on the rest of the thermal envelope. So what are typical weak points? For example, you can have beams in the wall. So let's say that beams are from the concrete or from the iron, and concrete and iron are better conductor than the insulator or the wood. Okay, so this is weak point. Then we have different kinds of junctions. We have wall roof junction, wall floor junction. We have wall window junction, and we have also lintels over the window, which are usually from the concrete, and the rest of the wall is from the bricks. Bricks are better. Concrete is better conductor than bricks. And finally, we have balcony slab. Balcony slab is very, very big problem, and I will explain the problem of thermal bridge balcony slab in more detail. Okay, so now we will concentrate on this balcony slab. So this is a cross section of the balcony slab. So let's say we have this reinforced concrete here, and we have walls from the brick here and here, and we have insulation on the wall. So what you see here there is no insulation. So if there is no insulation, heat will flow through this part which is not insulated. Okay, so this is weak point. Here we are losing most of the energy through this reinforced concrete slab. Okay, you can see the effect of this thermal bridge on this picture. This is interesting story because this building was additionally insulated just 1 year ago, and I made these pictures, and I was horrified to note that this bettering of the building was done very bad. Okay, so you see they put additional insulation on the walls, but they still let balconies to radiate a lot of energy. So you see balconies are very hot and they radiate a lot of energy, and of course because they are hot there is also larger convection. So we are losing much energy through these balconies because heat is going is avoiding the insulation, because so we must do something about these balconies. This is not how it should be done. Okay, this is example how it shouldn't be done, and I will tell you more about these problems later in the lecture. One possibility is that you also insulate balcony. Okay, so you lengthen this insulation until the end of the balcony, for example, of course. So the other, this is how you solve the problems if you have existing house. What to do if you are only building house? If you are building house, then you can also use so-called load-bearing insulation elements. So what is load-bearing insulation element? This is actually insulator, and this insulator is there are steel beams that are going through this insulation. So you see you have insulation and there are steel beams. Why steel beams? Steel beams are here so they can hold balcony in place. And why insulation? Insulation is because now heat cannot avoid insulation. So these things are very popular today. They were made in Austria. They are made in Austria and Germany because Austria and Germany are most advanced countries in the world regarding the building physics. And unfortunately, it is quite expensive But this solution provides such savings in heat losses that I believe that in long term you gain money, not lose money, by using this load-bearing insulation element. Okay, so now we were talking about individual parts of the building, and now the third part is we want to know complete losses of the whole building. So we will see individual contribution to the total thermal losses of the building. So this is one example of the building. You see that we have here different spaces. We have conditioned spaces. These rooms are heated and cooled. And we have, for example, garage. We are not heating and cooling garage. So usually this space is called unconditioned space. And of course, this dashed line, this is thermal envelope. By definition of the standard, it should be here. Okay. So what are individual components of the thermal losses? First, we have direct thermal losses. We were talking about direct thermal losses until now. This is losses through the walls and losses through the thermal bridges. So we see this is formula for walls. This is formula for thermal bridges. But direct thermal losses are not the only losses. We also have thermal losses through the ground, which also shouldn't be neglected. These thermal losses are much more difficult to calculate. Why? Because we have third temperature. We don't have only internal temperature and external temperature. We have also temperature of the ground. So it is not so simple to calculate these losses to the ground, and I will not show you the formulas. Okay, and then we have thermal losses through the unconditioned spaces. This is also difficult to calculate because we have temperature of the unconditioned spaces. So, for example, you know that in garage, temperature is usually lower than in the rest of the house. And finally, and this is a very important part, we have thermal losses through ventilation. And this is something that people often do not think about. So what is thermal losses through ventilation? What you do is you open window, and when you open window, the warm air from inside goes out, and you are getting fresh air, which is cold from outside. So where are losses? Losses are that you must warm up this fresh air which is coming from outside. You must warm it up to the temperature of the room, to the room temperature. Okay. So obviously these losses are proportional to the temperature difference, and they are also proportional to airflow. Airflow is here, and of course they are also proportional to thermal capacity of the air. Okay. So it is, from physical perspective, very simple formula. We will talk about this thermal losses of ventilation later. So please remember this. This is very important. These thermal losses through ventilation are very important part of the thermal losses. Okay. Now I will show you two practical ways how you can improve efficiency, which are not directly connected to the insulation. So first of all is that we can use heat pumps. Heat pumps are usually big mystery. People do not know really how they work, but they are not so much difficult to understand. Okay, so to understand this concept of heat pump, I will show you a difference between typical boiler furnace on the one side and heat pump. So what is the difference? So we start with what you know best. This is boiler or furnace. So what is the point of the boiler or the furnace? You are using fossil fuel. You are burning fossil fuels, and by burning fossil fuels, you create heat. So what you are actually doing? You are changing type of energy. You are changing from chemical energy of the fossil fuel into the heat energy. And of course, usually this efficiency is close to 100%. If this boiler or furnace is new. Of course, if it is very old, efficiency starts to drop. Okay, this is very important to know that efficiency is slowly dropping as these devices are aging. Okay, so for example, because if you put 3 joules of gas, you get 3 joules of heat. So you have 100% efficiency. On the other hand, you have heat pump. And heat pumps have coefficient of performance 300%. And how is it possible to have 300%? This is not logical. This is against our logic, okay? But it is not so strange. If I explain what is heat pump, in heat pump, we do not change from one type of energy to other type of energy. In heat pumps, we take heat from outside, where it's cold, and put it inside, where it's hot. This is against the nature, because we know that in nature, heat goes from hotter to colder. I showed you this, if you remember these videos before. But if we can use heat pumps, which transfer heat in the opposite direction, it transfers heat from the colder part to the hotter part. Of course, we must provide some energy so we can transfer heat, and we provide it by electricity. So the point of the heat pump is that you need only 1 joule of electricity to transfer 3 joules of heat. So this is why efficiency, better speaking, coefficient of performance is 300%, because we need only 1 joule of electricity to get 3 joules of heat. This is also only part of the story, because we know that we must produce electricity. And very often we are producing electricity from the fossil fuels. So what is the efficiency of production electricity in typical, I don't know, power plant? How much energy you need, how much chemical energy do you need in power plant to produce electricity? It happens that efficiency of power plants on coal are about 35 to 40%. So we are back on the square one, I would say. Not entirely. Why not entirely? Because I already told you, power plants can also heat. So you can, for example, heat part of the city. You can heat by waste heat, and the other part of the city you can heat by heat pumps. So in this case, this efficiency of power plant is larger than 35%. The other thing is, of course, that we can also produce electricity from renewable sources. In this case, of course, efficiency is not so important. Obviously, heat pumps make sense because, you know, in Sweden, 46% of installed capacity as space heaters is through heat pumps. So heat pumps are important part of this mixture of different solutions to our problems. The next important thing is so-called recuperator. I will tell you how we can reduce losses due to ventilation. So instead of opening the window and let the hot air to go out, we want that this air that's going out, we want that this air gives some energy, some heat to the air that's coming inside, to the cold air that's coming inside. How we do this? Oh, instead of opening the door, or often opening the window, we force this air to go through the pipe. So you see here inside, this is hot air from inside. It's going through the pipe, and in the end, it gets out. And we have fresh air from outside. It's going through another pipe inside, and it is warming up. Why is it this cold air warming up and this hot air cooling? Because these two gases are in thermal contact. So this hotter air from inside is giving heat to the colder air that is going outside, that is coming inside. I'm sorry. Okay. So this recuperator is so-called heat exchanger. This is more clever word for the recuperator. And in air-to-air heat exchangers have efficiency of about 60 to 80%. So 60 to 20% of energy can be still recovered by recuperators. Of course, recuperators do not make sense if you don't close the window. So very important part is also air tightness of the building. If you have a lot of gaps in the wall, for example, the walls are not done very properly, you have gaps between the window and the wall, then air will go outside and inside uncontrolled. You don't want this. You want to have perfect air tightness. You don't want that air is going uncontrolled through the wall. You only let that air is coming in and coming out through the recuperator. So recuperator must be always combined with air tightness. They always go together. You cannot use the advantage of recuperator without air tightness. Okay, so now I've told you about some interesting things that can improve energy efficiency of our building. And now we will put all these things together in building passive house. But before I use these different devices and mechanisms and we've learned so far, I must first define what is passive house. Maybe you heard about passive house. Passive house is a very popular term in Europe, and I see that that not many people really understand it. I know that my colleagues, civil engineers, don't understand it. So maybe it is not a bad idea that we try to understand what is this concept of passive house. So, of course, the concept was made up by two professors, one from Sweden and one from Germany, of course, because Scandinavia and Germany, as I told you before, are most advanced countries regarding the building physics. So they asked themselves, we know that we want to make some efficiency standard, building efficiency standard that will be true for all the world. But how can you do with this? Because, you know, in Italy, you have hot climate, you don't need a lot of energy for heating. And on the other side, you have, I don't know, Finland. In Finland, you cannot need a lot of energy for heating. So can we make universal efficiency standard? Is it possible? And they found a way. They found a way by starting from ventilation. Why ventilation? Both Italian guy and Finnish guy, they both need the same amount of fresh air. Why do you need fresh air? Why do you need ventilation and fresh air? Because you don't have any ventilation, then of course the air in the building becomes smelly, and of course you could even you can even die without oxygen, of course. So you need ventilation, and all people in the world need about the same amount of ventilation and about the same amount of fresh air. So they started by ventilation, and they said, what if we heat our houses by heating the air that's coming from outside? So we will not let any radiators, any convectors, nothing. This will be forbidden, and we will heat the house only by heating the air that is coming from outside. Now I will show you the definition. Passive house is a building for which thermal comfort can be achieved solely by post-heating and post-cooling of the fresh air mass, which is required to achieve sufficient indoor air quality conditions without the need for additional recirculation of the air. Very complicated, but it is not so difficult if I tell you with my words. So let's put some numbers into this. You have, it is assumed that minimum airflow rate is 30 cubic meters per hour per person. So we have enough fresh air for living. It is assumed that air can be heated for about 30 kelvins. Why 30 kelvins? We start if air is going through the recuperator, the air is heated to almost to the temperature of the room. Let's say it is heated to about 17, 18, 19 Celsius. And now you cannot heat it above 50 Celsius. Why not? Because if you have air at temperature above 50 Celsius, this dust in the air starts burning. So you get smell. So you can go beyond 50 Celsius. This means that you can heat the air only for 30 kelvins. And the third assumption is that typical floor area is 30 square meters per person. Okay, this is a little this is normal for perhaps for Germany and Scandinavia. It is a little bit a lot for Slovenia or I don't know, Croatia, because we are accustomed to smaller houses, don't have so much money. This is more culturally cultural assumption, not really, not really universal for the whole world. But let's stick with this definition. So if we put these numbers into the formula I showed you, I don't know, 5-6 slides before, we get that maximum allowable heat consumption is 10 watts per square meter of the house. And this is very small. This is really small. You will see that typically you have 100, you can have even few hundreds of watts per square meter in typical house which is not insulated well. So 10 watts per square meter is a very small consumption. So the question is it possible to do this? Is it possible? It is possible if we use all the knowledge I showed you until this point. So let's start with the empty house, and we will design it to become a really passive house. So what we must do? First of all, we must have low thermal losses. This is very obvious. We must lose a very small amount of heat. First of all, we must have good insulation. We must have thick polystyrene layers or thick mineral wool layers on the wall everywhere. Okay. So then we mustn't have any thermal bridges. So we must not have any space without thermal insulation, for example. Let's put it this simple way. And finally, in a passive house, we use triple glazed window. So making glass thicker makes no sense, I already told you. But making another glass makes sense. Why? Because when we have triple glazed window, we have 2 air spaces. Air space is the key. 2 air spaces is better than 1 air space. 3 glasses is the same as 2 glasses, but 2 air spaces are better than 1 air space. Okay, the second thing is we need efficient ventilation. I already told you, we need recuperators, we need air tightness. Air tightness, so no air is going out and in uncontrolled. We need a recuperator. So outside air goes through the ground and then goes to the recuperator. It is heated to about 18 Celsius. Then it is post-heated to 50 Celsius. And then it is let into the rooms. So you see, you don't need radiators because air is heating the building. You don't need water system for heating the building. It is air system that heats the building. So you don't need one system. This is also possible saving, of course. And you have exhaust air or waste air, which goes through the recuperator and cools down before leaving. Okay, and finally, we need efficient heating. First of all, we will heat the air not by furnace, but by heat pump. So we use heat pump to heat the air. And of course, we need solar gain. What we need is greenhouse effect. We are heating houses with greenhouse effect. We have big glassy walls or big windows in the south direction, because in the south direction there is sun. Of course, in Australia they need north direction, but in Europe, in Ukraine and the European Union, we want to have big glassy areas toward the south. So we get additional heating from the sun. Okay, so this was technical part. I will finish my lecture with some final remarks. I will tell you some legislative incentives in European Union, which are made in order to reduce thermal losses in buildings. The problem was recognized, of course, first in Germany and Scandinavia, and then through European Union, it is recognized as the very important problem in the whole European Union. So maybe this is also important because Ukraine, as far as I know, wants to come closer to European Union. So it is important that you know something about the trends in the European Union. So first we have a directive 2010-31 on energy performance of buildings. So what is the directive says? It says that member states must set up minimum energy performance requirements not very smart, but of course, people are forced to put more insulation on the houses. If you want to have a building permit, you must have enough insulation. Okay. By 2021, all new buildings should be nearly zero energy buildings. All major renovations must be done with energy performance upgrade. So if you are doing renovation, why not putting additional layer of the insulation? This is obviously a logical step. Okay, then the directive established energy performance certificates. Here is one certificate. Why is the certificate important? Because when you're buying a house and you see a certificate, and certificate says this house is not spending a lot of energy for warming, you might spend more money. Okay, so you know this is very efficient house. I will spend less money on heating, so I might buy it I might spend more money for buying it. So this is very important that we know how efficient are these houses on the market. There are also another financial instruments and measures. I will not go into detail. And we don't have one directive about this. We have two directives. The other directive is 2012-27, which is on energy efficiency in general, but it also has some points about performance of buildings. There is, according to this directive, there should be a strategy to attract investment in building renovation by member states. And also, interestingly, 3% of certain central government buildings should be energy renovated each year. And of course, there should be heat meters should be used in multi-apartment buildings. Why heat meters? Because you know, if you are living in the apartment in multi-apartment building, when you open the window, the extra heating will be paid by all building, by you and your neighbors. So you don't care really very much. However, if you have heat meter for your apartment, then you start thinking, well, if I open the door, if I open the window, then I will pay more. My neighbors will not pay more. So maybe I'm more inclined to save the energy. And actually, this principle has become true because the data showed that after heat meters are built in, people start spending less energy on heating. They start to behave more rational. Okay. So let me point, maybe this is interesting also, public funding on energy efficiency. So you see in European Union, about 5.5 billion euros per year are spent on building improvement, energy building improvement. So 76% of all public funding is going into building improvement. This is not very surprising. Why? Because you see in heating and cooling, there is big room for improvement. We have learned a few slides before that 30% of energy is going for heating and cooling. This is big room for improvement. Okay, this is why so much money is going here, because there is big opportunity to change something. Okay, and all others are very small. Transport 7%, industry 7%, energy supply is only 1%. So here we have chance to do something for better. And of course, maybe this is less interesting. There are different policy instruments. We have loans, we have subsidies, we have grants, we have fiscal incentives. So there are many financial types of public funding into building improvement. So let me finish with the last slide, conclusion. What are advantages, what we have learned? What are advantages of building energy efficiency improvement? First, I told you twice, now I'll tell you third time, there is biggest potential sector for energy saving. Okay, we can do a lot. We can really do a lot in this sector. And on the other hand, investment is low, because usually you don't need a lot of money to put additional layer of insulation. It is very cheap. It is. I'm already at point 3. It is relatively simple technology. of course, recuperators are more complex. R-tightness is also very simple. R-tightness is very simple technology. You don't need any big knowledge about R-tightness, okay? And of course, you can create new jobs in local industry. Producing insulation is local industry. You don't import thermal insulation from China. Why? Because thermal insulation has low density, and transportation low density materials does not make sense. So this is already local industry. And of course, when you put insulation on the building, this is local workers. This is not done by Chinese. This is done by local workers. This, again, you are increasing local industry. Building industry is local industry. And finally, I think that Ukraine already has some access to EU funds. You can take some EU funds for increasing efficiency of the buildings. I know that Slovenia and Croatia get some funds for increasing the thermal energy efficiency of the buildings. Of course, I must also tell you something about pitfalls, about energy efficiency improvement of the buildings. So I already told you, remember this balcony I showed you several slides before. Often this improvement of the building is done very, very badly. It is not done very as it should be, okay? So when you don't insulate balconies, you are still losing a lot of energy. You did something, but you didn't do your best. So if you don't do it properly, you are wasting money. And then the second thing is, of course, businesses, of course, they are not interested in energy efficiency. They are interested about making money, okay? So, of course, they will always try to do this improvement of the building for a lot of money and do it badly. They are not interested in good work. They are interested to make money. So, for example, typical example is you are trying to find some offers from the businesses, and they will not offer you insulation of the balconies because they will offer you lower price. So you will choose someone with lower price, and you will not know that you are ordering lower price. You are getting lower price because it will not be done properly. So what is the solution? The solution is that engineers and general public have some basic knowledge about these problems, so they can recognize that some business is not giving them a good solution. I know, for example, that in Slovenia, even civil engineers sometimes do not know all these details, and even they do not know how to do this properly. So I think that, and this is my point, this is why I have this lecture, it is important that we spread knowledge of these problems. So these problems are solved properly. Okay, I think this is all. I would thank you for your attention. I hope I was not, I was understandable for you all. Okay.
Okay, thank you very much for this lecture. Thank you very much for very interesting and clear information. And now it's time for questions. Do we have any questions from? Okay, the first one.
Thank you very much for a great presentation, and it was particularly interesting for me to go into detail on those temperature transfer bridges like balconies, because currently the building I live in participates in a German program for improving its energy efficiency, and so far we've been through the concept phase, and we have the biggest problem is that it's not a low cost initiative, so to say, as you mentioned, that it doesn't require lots of money. Because the preliminary calculation was for like 16-story concrete building, was that if we do comprehensive renovation, it will be like 460 euros per square meter. which is absolutely not affordable for because it will be like 50% of the apartment cost. So we'll probably end up with doing only part of the measures of those building energy efficiency measures because we just cannot afford it. Even if we have some external financing, it can be only like to 70%, which is quite good. But still, if we will only have to pay 30% of that amount, it will be unaffordable for most of the people who live there. So on what assumption did you base your statement that it's a low-cost initiative? Thank you.
Okay, it is obviously country dependent. Of course, houses are most probably much more expensive in European Union. I know that typical cost is in Slovenia, which is not very expensive. It's in Maribor, which is not very expensive. It's about 1,000 euros per square meter of the apartment. Okay, so this is the typical price of the apartment in Maribor, which is a very small town. 100,000 people, you know, from Ukraine perspective, this is a village. It is even more expensive in bigger cities.
But sorry, but 460 euros will be 50% of that price anyway, close to that.
Yes, but I'm talking about the floor area, and floor area is usually bigger than facade area in the building. Okay, so
yeah, but we were talking not about only you know, putting more isolation on the facade, but also doing all other measures like improving the heating system and windows, etc.
Okay, you are talking about the cost on the square meter of the apartment. Yes. Well, I don't know. Yeah. Yes, I think this is I'm not, you know, I'm not in business. I don't know exact numbers in Slovenia. It sounds a little bit expensive. Of course, there are incentives from incentives by the state in Slovenia. Slovenia is covering part of the cost, and for example, one of the reasons why people decide for getting additional insulation is that they have to color their facades anyway. So if they put additional insulation, there is no big difference just coloring facades and putting insulation. So what is interesting in Slovenia or Croatia, if you see Slovenia and Croatia, it is that each year these facades are renovated all over the place. So obviously people find it very affordable. Also, you should know that gas is much, I think it is much more expensive in Slovenia than in Ukraine. So when you have a calculation and you calculate how much energy you lose for heating, then of course you see that investment pays off in, I don't know, in 5 to 10 years at most, 5 to 10 years, because gas is so expensive. And gas is also so expensive because European Union wants to make gas expensive, so people spend less. You know? So they think about spending. You don't just open the windows. Okay, so probably when people decide about improvement, there are incentives from the state, and they make a calculation how much they spend on the warming and how much will they spend if they do renovation. They see. I know that they see that usually the investment pays off in 5 to 10 years. I don't know why is it so expensive, and it is maybe, I don't know if it's more expensive in Ukraine. I think it should not be more expensive. And I don't know what are your calculations, but it is suspiciously high number. What is in this number? Is there anything else, or only insulation of the walls?
You know, it was only like a preliminary concept, and probably they used some of the German prices because they didn't know the Ukrainian prices. But I think the material would be about the same because the cost of the material is probably not much different in Ukrainian and German markets.
But do you know these insulators is very cheap? The insulators are very cheap. The work is usually it is the work which is expensive, at least in European Union. Work is very expensive. To put these scaffolds, you know, and to pay wages for workers, this is usually expensive. The material is usually not the expensive part. Of course, if you did in your preliminary calculation, if there is some other things like heat exchangers or something like that, this is more expensive, of course. When I'm talking about low investment, I usually think about additional insulation. And of course, if you calculate how much you pay for heating and how much you will save for heating, if you calculate how much you will save in next 5 to 10 years, then you are on zero in 5 to 10 years. I'm talking about Slovenia and Croatia. I could not comment more because I should know more information. And I also don't know exact numbers in Slovenia either. I'm not in business. I'm in academia. Okay.
Okay, thank you very much.
Not provide more answer, more detailed answer.
Yes, we have more questions.
Yes.
Thank you for your election. When you spoke about the passive house, you say what there must be a good insulation of walls, which it mean be in watts per square meter for Kelvin degree. U coefficient, how much U coefficient it must be?
Yes, this is usually specified by state legislation, because you know that one of these their directives. Okay, I'm sorry. For building permits, you have state legislation, and for passive house, you have recommendations only. You don't have the details. It tells how much the U value must be. What you must do a calculation, and depending on the climate, of course, you must have lower U value in lower value in Finland and higher U value in Italy. So it depends on climate. It depends also within the country. It is not the same if you have in Italian Alps or you have a building in the south of Italy. So you must calculate the losses. You must you have special programs for this, PHPP, and you put everything in. You put in losses through the ground, losses, the direct losses, ventilation losses, and you calculate it. And if you are beyond 10 watts per square meter of floor area, then it is passive house. So I think that maybe there are some recommendations for different climate zones. This is possible, but the point is, if you want certificate your house to be passive house, you must calculate all losses. And also, I didn't tell you all the story, because there are also some details about saving on energy on light and saving energy on machinery in the building. So this warming and cooling is the biggest part of the passive house, but it's not the only part of the passive house. So, of course, I couldn't go into all details because I don't have enough time. I just wanted to concentrate on this part, which is talking about thermal losses. Yes.
Thank you.
It's about what you asked.
Okay, thank you. Any other questions from the audience? Okay.
Thanks. May I ask you about the heat pump equipment? How much does it cost? Is it on the market? Can we buy it? I just would like to know how much does it cost, really?
I'm sorry, I'm the wrong guy to ask this.
I don't have this kind of information.
Yeah, I have no idea. I'm just doing. I'm studying this stuff so I can introduce this stuff to my students. Of course, I'm physicist. Of course, I learned this stuff because I'm lecturer of building physics, but I don't have the numbers. I'm sorry.
But is it sold? Actually, is it sold?
Is it?
Is it sold? on the market? I mean,
Yes, yes, yes.
Yes.
Of course, I know that there are buildings, new buildings, which are in Slovenia at least, which use thermal pumps. My father, he recently installed a heat pump in his building, and he's very satisfied. He says, my electric bill is only a little bit larger, and I don't spend any gas." He's very happy. So yes, he has house which is 20 years old or 30 years old, and he installed a heat pump. So it is very popular. Yes, it is selling well.
so is heat pump? It's like recuperation equipment.
No, this is different. Two different things.
Oh, it's different.
Heat pump means that you are getting heat from outside. So instead of changing gas into heat, you are getting heat from outside and put it inside. On the other hand, recuperation means that air that leaves the house must transfer his heat to the air that comes inside. So these are two different concepts. Okay.
Thank you. Thank you.
Thank you. Okay, questions? We have several questions from our online audience, maybe, and you ask next, okay? So one question is, what is the amount of money that Slovenia has received over the years as help from the European Union for energy efficiency projects in absolute term and relative terms? So what's the amount of money for Slovenia?
Yeah, okay. Tough questions because I told you I don't have numbers. I can understand this. I could look it up, but I don't have this number from my head.
Okay, thank you. And another question: what if we should build our houses inside inside ground, so under the ground? What about energy efficiency? Would it be more efficient?
Well, it happens that ground temperature during the winter is higher than external temperature. So of course, there is in sense of losing less energy, it would be of course efficient to build all the house beyond the ground level. But then you don't have a light, of course. So yes, ground temperature is completely different story. I couldn't go into this because it's difficult. But yes, losses to the ground are smaller than losses through the facade because temperature of the ground is higher during the winter and lower during the summer. You know that if you have a cellar, the room beyond the ground level, you know that it is hotter during the winter. It is colder during the summer because of this ground effect. Yes, but of course, then you don't have light. Okay, so.
Okay, thank you.
What thermal insulation? What thermal insulation materials more using in Slovenia? Is it mineral materials like mineral wool, or it's some porous plastics?
It is usually it is equally used polystyrene and mineral wool. They are both used widely. And for example, typically they put 50 centimeters of mineral wool or polystyrene, or when they are adding insulation, they are typically adding 10 centimeters. So of course, Slovenia is more or less in the cold in the continental climate. But for example, in Italy, they use much less, okay? But Slovenia, typically, they use 10 to 15 centimeters, either polystyrene or mineral wool. They are using equally one and the other, depending on the house.
Thank you. Another question?
Thank you very much for the presentation. And I have a small remark that there are some measures that you can take to increase the efficiency, maybe some natural measures. For example, you can plant trees behind your windows, and you can have shadows in summer, and you can use the actually greenhouse effect in winter. So it's a very simple measure, but it can save much energy. And I have a question about, do you know, is there any dependence on the efficiency of the house depending on the number of floors in the house? So what are the optimal number of floors in the building?
Okay, so of course, trees, especially the trees that let leaves during the winter off, are very good, because during the summer you have shade, during the winter you have empty, and you have solar gain. There are many other things, of course. Where do you build? You can change micro location of your building. This also improves situation. Of course, you choose the situation where there is not very windy. Why windy? Because when you have wind, you increase convection. So of course there are many other things. I couldn't speak about all of them, and it all comes in the end to the radiation, conduction, and convection. So if you understand this, you understand different types. Then, of course, the study of shading. This is the completely new area. We could talk only about shading methods, and so on. Yes, you're right. This is only part of the story. What I told you is only part of the story, and depending on the time, we could talk about this for hours. And now let's go to number of floors. I think that from simplistic way, the important is the ratio between the facade area and volume of the house. So this ratio should be as small as possible, as small facade area, as big volume of the house. So this is geometry. You can calculate it yourself. Okay, so it is, of course, it is better to have. It is not good, for example, to have very high and very thin building, because it has big area and small volume, and it's also not very good to have very low and very large house, because again you have big area and small volume. It is best to have some kind of cuboid, so the all sides of this building are about the same. Then you have optimal minimum area of the facade to maximum volume. This is my approximate answer.
Thank you. Може хтось має питання українською, ми можемо перекласти. Ніхто не хоче. Добре. Then I have one question. Today I've read about a Ukrainian startup, about a guy who has started to build houses based on the Ukrainian tradition from straw and clay, соломи і глини. So what do you think about the energy efficiency of that type of buildings?
Well, I had diploma work a few years ago about this, the thermal efficiency of these buildings, and my student, of course, he did all the calculations. He also calculated financial efficiency. So how much energy, how much money you need, and he came to the conclusions that this building is equally efficient from financial aspect, as well from the aspect of thermal efficiency as the modern building. Of course, you must know what you are doing. Okay, this is the important thing. You must know the materials. You must use enough materials. You must. I think that if I remember right, straw layer must be thicker than layer of the mineral wool, because this straw layer is not just as efficient as as for example, mineral wool. Okay, so yes, it is possible, and there are also businesses in Slovenia which are already building this, and it is possible. Yes, it is feasible.
Okay, thank you very much. So that's all. Again, I want to thank you for this very interesting, very beautiful lecture, and maybe that's all.
Thank you. Thank you for inviting me to share my experience, my knowledge, and I hope that that this will improve the situation a little bit, and that this knowledge will get higher, because, as I told you, it is important that the things had to be done properly. It is not only about doing things; it is doing things properly. Because I have many situations in Slovenia which things are not done properly, even because civil engineers don't know how to do it properly. Okay, so thank you for listening.
Thank you, Marco. And
We are finishing the translation, but please do not leave us, Marco, yet. Витя, выключай это самое зв'язок. Ага.